Right, so going back, the charge naman, kanina ang trend is on the size. Now is on the charge. The higher the charge of your metal, the more acidic it is because the higher the charge on the central metal atom M, the strongly it withdraws from your oxygen. This increases the polarity of your O hydrogen bond, no OH bond, making acidic H, okay, making your proton a lot more acidic, thus a lot easier to remove, no? Easily to ionize, hence more positive because your oxygen here withdraws electron from your hydrogen. So comparing um, on this one, okay, your hexa aqua iron 2 plus versus your hexa aqua iron 3 plus. Now this one's ferric, this one is ferrous. Okay, comparing the charge, you should actually compute it. You should know that. Right, so you could actually compute for the oxidation of your iron right here. Remember that the charge of your water is 0. So 6 times 0 plus x plus 2 for the total charge of your coordination compound. You would have your ferrous iron. Okay, so you have x plus 6 times 0 equals 3 plus, because the total charge of your coordination compound right here is 3. So you have your ferric and ferrous. Okay, since ferric has one more a 3 plus, no, compared to your 2 plus, so ferric, no, or your hexa aqua iron 3 plus would possess, okay, higher acidity in your solution. Now for the transfer your oxo acids, okay, high electronegativity of your central atom E makes it easier to withdraw electrons from an oxygen of an OH group. This increases the polarity of your OH, making H more positive and easily ionizable. Okay, it becomes easier for E to withdraw electrons from O because it is more electronegative nga, which affects the electrons in the OH of water. Okay, the electrons are pulled more towards O, making acidic, making your H more positive, making it more easily ionizable, making it more acidic. Okay, so if you have an electronegative atom here, your your Z pulls more electron na to strongly against, okay, from your oxygen, making this bond a lot weaker. Okay, so if you have two oxo acids right here, okay, you could actually compare the central atom. Okay, the central atom for this one is chlorine, and this one would be borine. Okay, remember the trend for your electronegativity upward, increasing ang trend for your electronegativity. So chlorine is a lot more electronegative than your bromine. Okay, making this bond right here a lot weaker, making your 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 chloric acid strongly, no, or more acidic than your bromic acid. Okay, right, so I hope I'm being clear. So this one is more this one is more electronegative. Your chlorine is more electronegative than your bromine, making this compound a lot more acidic. Okay, so the trend for your oxo acid in terms of electronegativity, the higher the electronegativity of your central atom E, I'm sorry, the higher the acidity. Okay, alright. So your oxo acid naman, okay, the higher the number of your oxo acid in a molecular compound, the higher the acidity. Okay, so for this one, your perchloric acid is the strongest acid because it has the largest oxygen na attached to your chlorine. Okay, and the acid trend, okay, ang trend niya is this one to this one to this one and to this one, no? Hypochlorous, chlorous, chloric, perchloric. Okay, and this is your sulfuric. Okay, ito naman sulfurous mo. This one is your nitric, and this one is your nitrous, because this compound right here has more oxo group on it. Okay, looking back, you have your hypochlorous acid, no? Wala nga siyang oxo group on it. This is your chlorous acid. This is your chloric acid. Okay, and this one is your perchloric acid. Remember that this could actually form bonds right here. Okay, to resonate back. Right, so the more the oxo groups, the higher the acidity. Okay, alright, so in terms of resonance naman, um, oxo acid is more acidic if the resulting conjugate base is resonance stabilized. So what you need to do is to actually look for the conjugate base of your acid. Okay, so um So you look for the conjugate base of your acid, for example, sulfuric acid versus your sulfurous acid. So you try to draw the low structure for these two compounds and try to draw all the resonating structure. Okay. So pause this video and try to do that. Okay. Right. So note that this is the conjugate base for your sulfuric acid, no? And this is the conjugate base for your sulfurous acid. Okay, conjugate base kasi nawalan na ng proton. Right. So try to dot this the resonance structure of this conjugate bases. Okay, note that the conjugate bases of your sulfuric acid has three resonating structure. Okay, making this compound or sulfuric acid relatively acidic than your sulfurous acid. Okay, because it only have two resonance dito tatlo. This would be um the more acidic acid in this comparison right here. Right? So I hope I'm being clear. Okay, if you have any question, try to approach me, chat me. Okay? Okay, ma'am, hindi ko po gets, okay? Try, just chat lang, okay? Alright, so, sulfuric acid is more acidic than your sulfurous acid because it has three resonating structure compared mo sa dalawa ni sulfurous acid. Alright, so, actually, the acidity of your oxoacid can be described using the Pauling's rule. Okay, so the Pauling's rule um, estimates the pKa of your acid. Okay, so if you have a monoprotic acid, say nitric acid, um, okay, so you could actually use this pKa. So pKa equals, okay, approximately equals 8 minus 5 and times p, where p is the number of your oxo group on it. Okay, right. So if Q naman is greater than 1, meaning you have 3 ionizable group or net or 2, okay, you could actually use this one, right? Okay, after getting the pKa1, you could actually input in here and you get the pKa2. After getting the pKa2, you could actually input it and get your pKa3. Okay, kasi diba may mga polyprotic acid tayo. Okay, polyprotic acid in the terms of this one right here. Okay, sa oxo group. Okay, sa hydroxy dito. Okay, remember that we are talking about your oxo acid. Right, so for example, your hypoporous acid, your HP3PO2, it only has one oxo group. So you actually has one oxo group right here and one hydroxy, okay, acidic proton right here. Okay, so you can actually only use the monoprotic acid right here because it only has one acidic proton. So you use this formula right here, pK equals 8 minus 5 times 1 because it only has a length. Okay, it only has one oxo group. So 3 is the approximate pKa of your hypochlorous acid. So relatively acidic man din. So first thing you should know is actually to get the valence electron and try to distribute it equally, no, appropriately around your atoms. Okay, remember that your electronegative your least electronegative atom should be the metal or the central metal. Okay, so you could actually write your hypophosphoric acid in this formula right here. Okay, so one oxo group and one hydroxy, okay, acidic proton right here. Right, these ones are not acidic. Okay, because phosphorus is not an electronegative atom. Okay, right. All right, so carbonic acid is a diprotic acid, diba? It produces two hydroxide ion, two proton ions upon dissociation. So you actually can use the pKa2. So first off, you need to know how many um oxo group on it and how many um acidic hydrogens are on it. Okay, so drawing the carbonic acid should actually result into this one. Note that you have 2Q and 1P. Okay, so you can actually calculate the pKa1 muna, 8 minus 5 times 1 because you have one oxo group, kaya 3. You get the 3 right here, use it number 3, plus 5, you would get 8. That would be the pKa2 of your carbonic acid. Okay,